All right, so today we are going to finish our discussion on parametric equations and motion. On Friday, we talked about just plugging in some values and evaluating parametric equations. And then we looked at ways of writing a parametric equation as a function of y equals something with x, or x equals a function of y in that familiar way that we are used to seeing functions. So today we're going to deal a little bit more with motion. So Gary walks along a horizontal line, think of it as a number line, with the coordinate of his position in meters given by the equation s equals negative 0.1 times t cubed minus 20t squared plus 110t minus 85, where t is between 0 and 12. Use parametric equations and a graphing calculator to simulate his motion. Estimate the times when Gary changes directions. So in order to do that, we're going to pull up our calculator. And if you're jotting down these notes, I would say the important pieces here, Gary walks along a horizontal line. His position is given by that equation where t is from 0 to 12. And pretty much the rest. All right. So if we're in parametric mode, and we'll put our equation in, negative 0.1 t cubed minus 20t squared plus 110t minus 85. Then we do need something for our y equation. I'm going to use 1 and I know I want my window, my time goes from 0 to 12. Setting up my window. Now, unfortunately, with the way we graphed it, we can't tell when he changes direction. We don't know the time that it happens. So one thing we can do is go to our y equals and change the way it graphs. So if you arrow down and do the line, so it's got a line with a circle at the end, it will literally draw that. It'll look like a ball moving across the screen, leaving a trail. So if we then graph, Now we know the x value where Gary changed direction. And you can see he changed twice. He went to the left, came back to the right, and then went back to the left. But we still don't know the time where it happened. So the last thing that we can do is change the y. Instead of go 1, we're going to go t. And this should help us to find that value. And so everywhere it turns is where it changes direction. So, and we want the time when it happens. So we estimate. About 3.5 and about 9.5 would be a pretty good estimate. And that's probably, excuse me, probably in seconds. Excuse me. All right. So when we have horizontal motion or vertical motion, if we're only moving in one direction, we can write our equation either x equals or y equals. And generally it depends upon which way we're moving. If we're moving horizontally, x equals would be a great way to represent that function. If we're moving vertically, then I would use a y equals equation. However, if the motion is angular, in other words, we're moving both horizontally and vertically at the same time, we can use parametric equations of the form x equals v sub 0 times cosine theta times t, and y equals negative 16t squared plus v sub 0 times sine theta times t plus y sub 0, where v sub 0 is initial velocity in feet per second and y sub 0 is initial height in feet, and theta is the angle of the motion. All right, so here's an example. Kevin hits a baseball at 3 feet above the ground with an initial speed or an initial velocity of 150 feet per second at an angle of 18 degrees with the horizontal. In other words, it's going up at an angle of 18 degrees. Will the ball clear a 20-foot wall that is 400 feet away? And this problem reminds me of a certain twins.
This is the checkers game where grandson and granddad will bond. This is the kitchen where the...
All right, here we go.
Into deep left center for Mitchell, and we'll see you tomorrow night.
All right, so in a similar situation, we're going to use parametric equations. So x is equal to the initial velocity. And I'm going to put the t here So I don't confuse it. It's not part of the cosine function. And then our angle is 18 degrees. And for y, same thing. I'm going to put the t with the initial velocity. All right. So what I'm going to do is I'm going to, first of all, try to find a way to draw that, that wall that's 400 feet away. Well, the good news is I know a little bit about how to do that. So I know I want the horizontal distance to be 400 feet. The vertical distance I'm going to go 0.05, oops. 20 times 0.2 t should work, and then I'll limit my value for t. 150 t times cosine of 18 and negative 16 t squared plus 150 t sine of 18 plus 3, because it started 3 inches above the, or 3 feet above the ground. And again, I'm going to use that little ball graph. See if I can get that to work. Now, I've got that. I want to check my window. I don't need to go from 0 to 12. I think I can do it 5 seconds. I think that should be enough. X, we want to be able to see that fence. So and Y, I don't know where we go. 40 feet, count by twos. And we can see the ball does not hit the wall. It hits the part way up the wall. So not, it's not going to be a home run. No. Ball does not clear. And your assignment. 38, 40, and 44 on the same handout that I gave you on Friday. Just to be the bottom of the front side and a couple problems on the back side.